Welcome to a reading from the Lucasian Legacy, the Lucasian Professorship of Mathematics at Cambridge University, 1663 to 1993, by Robert Bruen, as read by his son, Garth Bruen. Sir M. James Lighthill, 1969 to 1980. I think the subject I became interested in above all was mathematics. I am a mathematician fundamentally. Although I have done many other things, I became very interested in mathematics at a very young age. I can never remember not being interested in mathematics, certainly at the age of 3 or thereabouts. Sir M. James Lighthill. Sir M. James Lighthill, born 1924, like many mathematicians, was fairly precocious and always ahead of his age group. Fortunately, the schools he attended allowed him to learn alongside people who were considerably older. He went to one of Britain's famous schools, Winchester College, winning a scholarship there at the age of 12. Another boy there the same age was Freeman Dyson. The two boys studied together and again managed to persuade the teachers to allow them to study differently from their age group. Studying mainly from books, they won major scholarships to Trinity College, Cambridge, at the age of 15. This was the much younger than normal Cambridge practice, and Cambridge did not want them to enroll until the age of 17. In some respects, this was good for both of them. They continued to study mathematics with great enthusiasm, but it gave them time to study many other subjects. Lighthill developed a strong interest in languages at the same time. Both were able to pursue the study of humanities as well as mathematics because they had extra time before going to university. They had continued to do mathematics, so when they arrived at Cambridge, it was not necessarily to study the undergraduate material at all. During the war in 1941, there was a rule that no one could have more than 2 years of university education. After that, students were expected to engage in the war effort. Bright students were managing to get the bachelor's degree in 2 years. There were very few other people going to the postgraduate lectures that Lighthill and Dyson attended. As a result, Lighthill and Dyson had become the greatest mathematicians almost to themselves. Sometimes there were only 5 students in classes given by G. H. Hardy, J. F. Littlewood, P. A. M. Dirac, A. S. Beskovich, and many other top mathematicians. The ones that taught him most were Hardy and Littlewood, both great mathematical analysts. Both believed that their work was only of importance for its own sake and because it was pure mathematics, incapable of being used for anything. A famous book by Hardy called A Mathematician's Apology was written to make this point. Throughout his career in applied mathematics, Lighthill found that the training in basic analysis was endlessly valuable and important. He remembered telling Hardy that he found what Hardy taught him to be valuable in applied mathematics, but he did not think Hardy believed him. After 2 years at Cambridge, Lighthill entered the war effort, joining the aerodynamics division of the National Physical Laboratory. He was put under the charge of Sidney Goldstein, an applied mathematician. Goldstein was typical of the applied mathematicians Lighthill would have studied under at Cambridge had it not been for the war. Lighthill had not encountered such a first-rate applied mathematician while he was at Cambridge, with the exception of Dirac. In 1943, Goldstein told Lighthill that the authorities believed that the war would go on for such a long time that the British would end up having to have supersonic aircraft to fight the Germans. Lighthill was given the task of finding out everything known about supersonic aerodynamics and take it from there. He read the works that had been done by German Prandtl, Bussmann, Italian Crocco, and Swiss Accaret scientists. Lighthill wrote many papers on supersonic aerodynamics in the first year that developed the ideas about what supersonic aircraft might be like in the future. There is a tenuous link between the ideas that were coming out then and the ultimate shape which the Concorde finally took. Lighthill was deeply involved when the Concorde came about because of the time he was director at the Royal Aircraft Establishment. While he was working on other things with Goldstein, the war abruptly ended. Lighthill had learned a lot during the 2 years in the war effort in applied mathematics, but he had felt terribly frustrated because he wanted to be a pure mathematician. When the war was over, he thought to himself, "Now why don't I go back and do what I was meant to do?" All his life he had wanted to do mathematics, especially pure mathematics. He returned to Cambridge, submitting to Trinity College the 12 papers he had written while at the NPL. He was granted a fellowship at Cambridge, which allowed him to do research. He spent only a short time pursuing pure mathematical research because he found people writing him letters about the papers he had written while at the NPL. For example, G.I. Taylor, one of Britain's greatest mathematical scientists, had questions to ask him, as did Goldstein himself. Lighthill received the greatest challenge of his life in 1949 when the Ministry of Aviation asked him to determine if jet aircraft developed originally for military purposes could be used for civilian purposes. The problem was whether they could be made tolerable to communities living near airports. This has turned out to be one of the abiding preoccupations: how jets can be made quieter and how more powerful at the same time. Lighthill started working on that problem, and the resulting paper, published in 1952, is one of the most cited papers in aerodynamics. In it, Lighthill reports his eighth power law of jet noise that says there is a tendency for the acoustic energy emitted from jet engine to vary as the eighth power of the jet exit velocity. This knowledge made quieter engines possible, since those early days jet aircraft had become increasingly quiet, making the whole development of jet transport possible. This is one area of work where Lighthill is still involved. When Goldstein became president of applied mathematics at Manchester University, Lighthill joined him and continued with his work. Goldstein put together a splendid team of people. Then suddenly Goldstein was taken by the call to Zionism. In 1950, he moved to Israel, where he assumed the top academic post at the Technion, the technical university at Haifa, and Lighthill was chosen to succeed him as the professor of applied mathematics. For the next 9 years, Lighthill headed this group of applied mathematicians. He had the first-rate laboratory called the Fluid Motion Laboratory, which had good supersonic wind tunnels, shock tubes, and low turbulence tunnels. It was well equipped with separate people to run the experimental equipment. Lighthill returned to the study of birds, starting new work. He had already worked with incompressible aerodynamics, or low Mach number aerodynamics, and with supersonic aerodynamics, but he had done nothing in between. He started some pioneering work in transonic aerodynamics, an interesting and more difficult field. Subsonic aerodynamics utilizes Laplace's equation, boundary layers, and such concepts. Supersonic aerodynamics utilizes purely hyperbolic equations and boundary layers, but transonic aerodynamics utilizes equations of mixed type. Lighthill invented a new method based on certain holograph transformations and mapping the problem onto a different problem which could be solved. He worked on that and on more extensions of the supersonic work to more complicated problems, like delta wings. At the end of the 1950s, Lighthill was unexpectedly invited to direct the Royal Aircraft Establishment at Farnborough, an enterprise with almost 8,000 employees. Its mission was like that of NASA Langley, a sort of overall aeronautic research establishment with outstations in main base located at Farnborough. There was an important airfield at Bedford with large supersonic wind tunnels. The RAE had departments covering everything from chemistry to electronics, but its main work was centered on aerodynamics and structures. The Harrier, the vertical takeoff aircraft, VTOL, was at the development stage, as was the Concorde. Britain was moving forward as fast as possible in space science. While he was there, he could not actually do research himself, but it was perfectly feasible for him to write long review articles, because good biographical services were at his disposal. These review articles were not just summaries of other people's work, but rather his own view of it. Some of his best reviews were written during this period. After about 5 years, he felt that the time was right to move on to other subjects. One was oceanography, which has gradually expanded to become the science of the Earth's fluid envelope. He likes the phrase because it includes the atmosphere, the oceans, the groundwater, the rivers, and the lakes. Then out of the blue came this offer to him to be a candidate for the Lucasian chair when Dirac retired. He thought the people in fluid dynamics at Cambridge felt they would like him to be a candidate because Sir George Gabriel Stokes had been a great Lucasian professor. Dirac had been professor for almost 40 years, but Stokes had been Lucasian professor even longer. Lighthill was elected in April 1968, although Dirac was not due to retire until October of 1969. Lighthill considers these years to have been splendid 10 years, when he could concentrate entirely on research. There were no administrative or other duties attached to the post, except to generally reside during the term within 5 miles of the Great St. Mary's Church. Lighthill mainly concentrated on fluid dynamics research and writing books. His major book, Waves and Fluids, includes acoustics, oceanography, water waves, and atmospheric science, and internal waters in the atmosphere. He also has a book on mathematical biofluid dynamics. His bestseller is an